Welcome back. Last time we added planes to our Raytracer. This time I want to do some solid modeling. In solid modeling we can treat our objects as solids and we can do operations on them. For example, we can do a union to combine two objects, or we can do an intersection to take the object where both solids are present, or we can take the difference, that is, take away one object from another object. And in solid modeling we need all the hits of an object, so if we send a ray through objects we will keep both the enter point and the exit point of all objects that are part of this solid object. So let's start by creating a new file. We'll create a solid interface. The solid interface will be the equivalent of the shape that we had before. So we will have a function that takes a ray and finds all the intersections of our solid. The intersections would be a list of pairs where the ray will enter and exit our solid object. So a pair we call a range, and it will have enter hit and the exit hit. We call them H1 and H2. And the solid hit will have the t value, the distance from our ray origin. Now let's add solid to our sphere, so we can treat the sphere as either a solid or a shape. And the algorithm for hitting a solid sphere will be almost the same as when we're looking for just the first hit. If we miss it, we will return a solid miss. Let's create it. And if we hit, we will return a solid hit range, that is where we enter the sphere and where we exit the sphere. And let's make solid hit range implement intersections, so we can treat it as the simplest form of an intersection. We also need a way to convert our solid into shapes so that our Raytracer can use them as shapes when we render. So we create an object for that takes one solid and converts it into a shape. And converting a solid into shape is kind of just finding out what is the closest hit to the camera. So we take all the hits and find the first one that is an actual hit. And when we find the closest hit, we return it as a surface hit. We do need the normal calculation for a surface hit, so we add that to our solid hit. Let's now let's try it out in our tracer. Let's create just one solid shape that is our sphere and try to render it. Of course, we need to add the normal calculations to our solid hit in the sphere. And now we can see our sphere as a solid object. Let's zoom in a bit. Just as we could transform shapes, we also want to be able to transform solids. So let's add classes for that. Transformed solid will take a solid and a transformation. And in the intersections function, we will take we will transform our ray just as we did for the shape, and the resulting intersections also need transformation. I'll create an extension method for it. That will return transformed intersections. We do need a solid intersections object that we can return. It will implement intersections and will just take a list of hits in. So we take our hits and transform each of them. For each hit in the range, we transform it. We also create a function for transforming a hit. T will stay the same, but the normal calculations will change. So we transform the hit point into the solid object space, and then we calculate the normal and transform the normal back into view space. Now we can use it to transform our solid objects. For example, we can transform our sphere. Let's move it a bit up. Here we have two solids, one transformed and one at the original position. Now let's create a few static objects that we can use for our operations. Three spheres. And now we're ready to implement our solid operations. Let's start with the solid union, which is the simplest one, where we just add up two objects. Solid union will take two objects, the object 1 and object 2, and it will be a new solid. In the intersections function, we will calculate all the hits for both objects. And we add them together in one list. And we also sort the list so we make sure that the closest hit is first in the list. If the list is empty, we have not hit anything, so we can just return a solid miss. Otherwise we could just return all these hits that we have found, but this will contain a lot of hits in the middle of this object, which we don't want, so we need to remove them. Go through them one by one, so we start with taking the first one, and then we loop through all other objects in the list, and if the last checked object, which is the last one in the results list, overlaps with the current object, we need to remove some hits, and we need a method for checking if two ranges overlap. Let's put it in the solid hit range. So if a hit is within this range, we will return true. And if two ranges overlap, we have to remove the one that we are checking for and replace it with a new range. and the new range will be the extent of both overlapping ranges as one. And that's all we have to do. We just need to return the results, and we should be done. Let's move the object up a bit. And now we can treat these two spheres as one. We can transform it. We can add a material to it, just as if it was one object in our world. Let's implement our next operation, the solid intersection. That is taking only the object where two objects are occupying the same space in the world. So just as for the union, we take two objects and return a new solid. The algorithm is a bit different. We first find all the hits for both objects and make sure they are sorted. If either of the lists are empty, we are outside the colliding space, so we ignore it and just return a solid miss. Here I just return hits from the B if we are in there, but we actually need to find out which is our actual hit to make the normals correct. So we loop over both lists, and if the lists are overlapping, we will take the minimal part of the both ranges. So we find the last of the starting points, and we will also find the first of the exit points. And that will be our new hit range. There we have the intersection of our two spheres. Let's create our third operation. It's the solid difference. It is when we take two objects but we remove one of them from the first one. as usual, we have two solids, which will result in a new solid. We start, as usual, by finding all the hits for both objects. If we don't have any hits on A, we are outside of A and we don't care about it, so we call it a miss. And if we are outside of B, we can just return whatever hit we have from A. But if we have hits both from A and B, we have to figure out what is our actual new hit points. We will start with an empty list and go through the hits in the B. If a hit range from A contains both the hit from B, then we add two new hits that will take away the middle part where B is. Else, if A contains only the start hit of B, we just remove that part of the from the A hit range, and vice versa if it contains the endpoint of B. And the last thing we have to check is if B is outside of A, then we just take A. Now, when we render it, we see that the object looks like it's been carved out, but the normals in the carved out section are wrong. They need to be inverted. So let's do that. So all hits from a B object, we need to invert the normals. And to invert the normal, we just take the same t, but for the normal calculation we calculate it and then invert it. There, looks much better. We do see that on our union object we have some artifacts on the shadow. Let's fix it. We have, up until now we have filtered away all t's or hits that are outside our range, but to make it a better calculation, let's send it into the intersect method. So instead of checking if it's larger than 1, we check if it's actual inside our range. So do it here for the sphere. And for the transformed shape, we just send the range along, and the same for the shape with material. Let's also fix the plane. If it's inside the range, it's a hit. And also for the solid shape, we have to do the same. If any hit in the range is inside the range, it's a hit. Much better shadows. Let's remove one more sphere from our bottom object. And it will look like a ring. Let's extract it to a variable and call it the ring or ring. Now I want to duplicate it and I want to rotate it. And rotate is a new transformation that we have not used before, so we have to create it. So let's rotate it 90 degrees, and we add the new transformation to our matrix object. It will be just as the other, we just call into the matrix library with the angle. And since we are in this file, let's also add methods for rotate X and Y. Here, since we rotate after translation, it will rotate it like that. And if we rotate it before the translation, it will be rotated in place. And to make it a bit clearer, I will remove the Z values here. And we can see our three operations: union, difference, and intersection. Thank you for watching.